we have, because of that tropical storm Zeta that came through, we're having random and widespread internet outages. So that's what I've been dealing with today. And I'm trying to use a hotspot so we can at least talk and meet. And then, of course, within 3 minutes of class starting, it fails on me. So that's why all that craziness was going on. But I am up and running. I see that everyone's got their answers in. I'm going to lock. So looks like I'm seeing them come in. At least 2 people got it right. 3 people. 4, I'm guessing everyone. So eigenvalues are the, if you have an upper triangular matrix or any triangular matrix, whether it be upper or lower, eigenvalues are just going to be those elements on the diagonal. So 1, a -3, and a +2. And even if you'd have gone through and done the calculation, right, you would do the easiest way to do that would take the determinant on the final row. So just trying to quickly get my iPad in here to write it out. But then you'd see you just get a 2 minus lambda, and then you get a -3 minus lambda, and then you multiply by 1 minus lambda. That would be your characteristic polynomial, and that'd give you your characteristic equation, which then you can clearly see the roots are 1, -3, and 2. So y'all are good on that, which is awesome. Any questions?
Not really a question, but I just kind of figured like when we were doing determinants, because they had all the zeros below it, that it was all linear numbers.
Mm-hmm. Yeah. So that was the other thing, right? Once we had the determinant of an upper triangular matrix, it was just the product of the diagonals. 100% correct.
So if you was to multiply the diagonal, you would get one single eigenvector. I mean eigenvalue.
So remember, you're not multiplying the diagonal elements of this matrix to find your eigenvalues, right? You got to multiply. Let's see. You got to connect to the right internet. Let me get my iPad in here so we can write. Remember, it's that a minus lambda I, which is what we're taking the determinant of. So in this case, it'd be, we're taking the determinant of 1 minus lambda E2, 0, -3 minus lambda pi, 0, 0, -2 minus lambda. That's the determinant of the matrix that we got to take to get the characteristic polynomial, and those are eigenvalues. But here again, like Chevy pointed out, right, you have that nice upper triangular matrix still, then this is where you'd be multiplying the diagonal elements together to get your determinant. So it'd be a 1 minus lambda times a -3 minus lambda times a 2 minus lambda. All right, any other questions? I don't think I'm frozen. I think I'm still here. I see Chevy moving, so that's a good sign. So yeah, all right. So we're gonna move on then. Okay, so today, do an example, talk about a little bit more theory that's gonna set us up for next week, okay? So you're gonna have to find the eigenvalues and eigenvectors of the matrix A, which I want that to actually look like an A. And it's going to have the entries 1, 5, -3, and 1. Find the eigenvalues and eigenvectors. So first thing I want you to do, I want you to try to work on this on your own for a little bit, but I just want the first step to be done. I want you just to, right now, find the eigenvalues. Okay. Once we make sure everyone's on the same page for the eigenvalues, then we'll find the eigenvectors. Let's go ahead and take a moment and try to find the eigenvalues for this. And the one thing I want to remind you of is that for our eigenvalues, we haven't ever said whether or not they needed to be real numbers or imaginary numbers. Real numbers or imaginary numbers. We've never put a restriction on what they could be. Yes. Okay. And give me a thumbs up, whether it's through video or the emoji. You think you got them. All right. I'm going to give you all about one more minute. Like I said, give me, if I might not have been paying attention. Give me a thumbs up now if you're done. If not, that's fine. Keep working. All right. Now I'm unmuted. All right, I'm going to give you all just one more minute. Just one more minute. All right, I'm going to ask one more time. Thumbs up if you think you got it. So no one's got it? Let me ask this. Thumbs up if you got to the characteristic equation.
Yeah. You get to I. That's where you need
Yeah, I got there, but I got lost afterwards.
you get to no real answer, so you have to come in and explain what we got.
Cool. So that's why I was giving you a hint. Eigenvalues, it doesn't matter necessarily whether or not they're real or imaginary. Okay, so what do you get the characteristic polynomial to be? Well, take the determinant of my matrix minus lambda times I, which gives me 1 minus lambda quantity squared plus 15. And if I FOIL out that 1 minus lambda squared, add 15 to it, so it'll be lambda squared minus 2 lambda plus 16.
That's where I stopped and I got lost.
All right, so we're trying to find the.
Back out.
Sorry, go ahead. Go ahead.
I know I'm supposed to factor back out from this, from your final equation you have so far, but I just got lost afterwards.
Awesome. I'm glad we're going through this. So our goal is to figure out when this polynomial, this characteristic equation, is equal to what? Yeah, 0. Thank you, Chevy. Right? Find out when it's equal to 0, because we want to find out when that determinant is equal to 0. So one of the things in what all we've kind of been exposed to so far, especially if you haven't attempted any of the homeworks, which I know a lot of you haven't yet, right? Then I would want to try and factor. Right? That whenever we're giving a quadratic equation, one of the first things we want to find the roots or find the zeros, we want to factor. But can I think of two numbers that when I multiply together, I get 16? But when I add them, I get to -2.
4.
All right, so 4 and what? Well, the only thing I can multiply 4 by to get to 16 is 4. All right, if I add those together, I get a +8. And even if I did -4 or -4, the sum is a -8. So 4s won't work. What are some other options? What are other factors of 16?
All right, so you have 1 and 16, you have 2 and 8, you have that's all the factors of 16?
Yep.
Yeah, I think that's
Those are all the factors. And we see that none of them add up to -2. Does that mean that this quadratic has no roots?
Yes.
Not at all.
No real roots.
Not necessarily.
No
In this case, it
real.
won't have real roots, but it just doesn't have any nice, simple roots.
Well, that's what I just said. No real roots, and you said no.
It said no simple roots. It could have real roots.
Mm-hmm.
So just because you can see where the answer is, you can say no real roots, right? Trying to say if we're looking at this without knowing what the answer is, all we're saying is that we know from just trying this factoring and seeing that it fails that it's not something simple. But what was the foolproof thing that I can always use to find my roots of a quadratic equation?
You use your
Quadratic formula.
Yeah, quadratic formula. So, and remember, quadratic formula tells me my roots for any quadratic equation, -b plus or minus the square root b squared minus 4ac all over 2 times a. Hey, all that algebra that you learned is important, not just in calculus. It turns out it's also important in linear algebra. And remembering where this is for polynomials, quadratics of the form a times your variable squared plus b times your variable plus c. So for the equation I'm trying to solve, my a is 1, my b is -2, my c is 16. So just plug it into the quadratic formula. So then the roots for lambda squared minus 2 lambda plus 16, well, it's going to be -b plus or minus b squared minus 4 times a times c all over 2 times a. And then my goal from there is to just simplify it. Okay. So I'm going to have positive 2 plus or minus square root of 4 minus, let's see, 4 times 16. 6 times 4 is 24, so 64. All over 2. Right? And one of the things I always like to coach my college algebra students on is we can take it in small little pieces, right? Do the calculations that we see that are easy to do and just start simplifying down over a period of time what we have. Well, this would be equal to 2 plus or minus the square root of negative 60 over 2. And what you're usually taught in your algebra courses, once you see a negative under the square root, you're supposed to stop. But they always take you through this extra section where it's like, oh, well, there are such things as complex numbers. Complex numbers are where we deal with a negative under a square root. And that's where we bring in this variable. Well, it's not really a variable, it's a letter, call it I. We always reserve I to be equal to the square root of what?
-1.
Yeah, -1. And once I do that, then I can take something like the square root of negative 60 and say, hey, the 60 part, I could probably take the square root of, or at least reduce that down. That negative is what's messing me up. So we can just pull it out, and because we can split radicals over multiplication, because thanks to our exponent laws, square root of negative 60 is the same thing as the square root of -1 times 60, or I times the square root of 60. And then I say, okay, now I can start attacking that square root of 60. And can I pull a perfect square out of that?
I'll leave 4. 4 times 15.
4 times 15, perfect. Which means this is going to be a 2i times the square root of 15. Square root of 15 can't get reduced. There's no perfect squares, it's factors of 15. So that means in blue, we just kind of went off to the side, did some scratch work. This is 2 plus or minus 2 times I times the square root of 15 all over 2. What does that reduce to? I think you all should be caught up with the writing. Yeah, go for it, Josh.
Is, I'll guess, 2 plus I square root 15.
So there wouldn't be a 2 there up front because I would split this division over that plus minus sign. So it'd end up having a 2 divided by 2 plus or minus a 2i square root of 15 divided by 2. So it'd actually be a 1 plus or minus I square root of 15. So you got the second part correct. It was just that first part. So then this gives me my 2 eigenvalues. Eigenvalues are 1 plus I times the square root of 15 and 1 minus I times the square root of 15. Now, whenever you're dealing with eigenvalues, having complex eigenvalues is usually not a good sign for your matrix, but it is something you can have. So that's why usually, especially when you see examples, if you're looking up other resources, they're going to occasionally have imaginary eigenvalues appear, but most of your examples are with real eigenvalues because that's what we want. We want real eigenvalues. It's easier to talk and interpret them when they're real numbers versus imaginary numbers. but we can still, the point of this exercise is that we can still get imaginary eigenvalues. So let's rewrite everything, just kind of get our summary. So we had the matrix A, which is 1, 5, -3, 1, has eigenvalues lambda 1, 1 minus I times the square root of 15, and lambda 2, 1 plus I square root of 15. So those are our eigenvalues. Everyone good so far? If not, please ask a question or just give me a thumbs up. All right. So now that we have that, next thing I want y'all to do is find that eigenspace for lambda 1. Find that eigenspace for lambda 1. And even though that eigenvalue is now a complex number, the process does not change one bit. Process does not change one bit. Sorry, heard someone come at the door. Just in case you were stuck sitting there, that is how we start this off, right? Want to find what my x's look like, what the solutions to this matrix product looks like. What's that face for, Chevy?
My brain just died. I don't know what to do.
So whenever back in the day, so many months ago, right? When I was trying to solve for the solution to any matrix system, this AX equals B, we created a what matrix? It starts with an A.
Augmented.
Augmented matrix. What do we do to that augmented matrix to find the solution?
We row reduce it.
Yeah. We'll reduce it. Same thing is going to happen here.
Okay, I have a question. I just want to make sure I have the right idea about going about this.
Mhm.
Okay, so to reproduce, right, you would okay, say for instance we try and get rid of the 3 in row 2. You will have
Right.
to
So
multiply. Whoops.
first up, and well, let's just, you're going to lead me through it then. How about we do that since we need to move on a little bit anyway? Let me actually go back to the other screen. So this becomes this matrix right here. I'm underlining in red. What does that simplify to? So specifically this 1 minus 1 minus I squared of 15, what does that become?
Has to become a 1.
Through row reduction, yes. I'm talking about, I'm just doing in that entry, that arithmetic that I do there to simplify what I see. What am I left with?
And you left with just a negative I square root 15.
Close, not negative, it would be positive. Because I would take 1 minus I squared of 15. When I distribute that negative sign through, choose that from a minus to a plus. It'd be 1 minus 1 plus I squared of 15. But you had the core content correct. And you see that's also the case in the bottom right entry. Right? So this is going to be the matrix that I need to row reduce. So now that we have that for everyone, we had I squared of 15, 5, negative 3I square root of 15. You can augment this with zeros, but that last row doesn't ever change. So if you want to leave it off, you're more than welcome to. But Josh, you're trying to ask me a question before I stopped you, and now I'm going to finally let you ask your question. What do you want to do there to row reduce it?
Okay, well, what I was going to do was okay. Well, skip that. What we're going to do. So to reduce, right, you will have to multiply say the 3, you multiply it by I root 15, and then you multiply I root 15 by 3 to get that 0 there.
All right, so I see you. Here's what I hear you saying. Row 1 is equal to 3 row 1. Row 2 is going to be equal to I squared of 15 row 2. Right, so I can kind of get those numbers to be the same. So then I'll have a 3I squared of 15, 15, 0. Negative 3I squared of 15. And then, question for everyone. Just coming off to the side to do that last calculation. What is I squared of 15 times I squared of 15 going to be?
Perfect square.
Perfect square, yeah.
Don't we
15.
have to turn the? Don't we have to find a pivot first?
So this is on the process. We're trying to just complete this row operation. But your pivot, you can, sorry, Nabari, go ahead. What is it? Whoops.
No, just saying 15.
So close. It's not 15 actually. It's going to be negative 15. So square root of 15 times square root of 15, the square roots do cancel each other out and leave me with a positive 15. But I got to remember, I'm also multiplying two i's together, which means this is the square root of negative 1 quantity squared. Square and square root would cancel each other out, and I'm left with a negative 1. So I'll get a negative 15 in that bottom right hand corner. Okay. So now that I got that, Josh, what's next?
I'm not really understanding why you're doing it like that.
Well, it doesn't really matter. So your row reduction is just, you can apply row operations to get to the same end goal. Right? If you're solving an algebraic equation, is there one and only one way to go about solving it?
Yeah, but that's still more difficult than just finding your pivot though.
Depends on who you are. And you'll see though, because what do we have here? Row 1 and row 2, very well related, right? Row 2 is just the negative of row 1. It also kind of gives me a hint. And as we've seen with a lot of our when we're trying to find eigenvectors, when we're row reducing this stuff, we're going to get a free variable. And we're going to get row zeros. So if you come to the same answer, Eliam, as what Josh is getting to, or going to get to, and I can even tell you I did it differently in my lecture notes. And I'm doing it differently than I think what you're probably doing. As long as we all get to the same answer, it's fine. So Josh, what is your next step?
I'm gonna be row 2 minus row 1.
So then that gives me 3i squared root of 15, 15, 0, 0, 0, 0. Which then I can convert back into a system of equations. So this is 3i squared root of 15 times x1 plus 15x2 has got to be equal to 0. And my x2 is what type of variable?
Oh, wait. Made a mistake.
3.
Made a mistake. It's supposed to be
Or
row
plus.
2 plus row 1, not minus. Yeah, that's it.
I didn't check it because we got to where we wanted to go. But yeah, no, good catch. X2 here would be a free variable. Right? So then I can solve for x1 with respect to x2. It's kind of coming down here a little bit. And x1 would be equal to, I guess you might not see it. You just block this off so we can figure out how to write x1 in terms of x2. So I'd have a 3i squared root of 15 times x1 would be equal to negative 15 x2. And then to get x1 by itself, I need to divide by this 3i square root of 15. Which, if you do some simplification and mess around with it, you should get what is it? Let me find it again. 1 minus, so it'll end up being a, actually, let me just do it all at once so I don't second guess myself. Square root of 15 x2 over 3i. Bring the I up, which cancels out that negative. So this is what x1 has got to look like. wherever you choose x2 to be, and there's slightly different ways you can write it. I just kind of messed around with it a little bit so I can get all radicals out of the denominator. I is technically a radical. And I'll trust that because I want to move on to something else. I'll trust that you can at least work through on your own time on how I get there.
How did you get rid of the square root of 15 and the 15? Like, how did you put that to the top?
X divided by the square root of x gives me what? X divided by the square root of x gives me what, Chevy?
Square root of x?
Mm-hmm. So then 15 divided by square root of 15 gives me square root of 15. It's cool. Like I was saying, it's some of this algebra do on your own because it's not necessarily super easy to pick up on, but I'm just trying to make sure that we're moving on. So then that means any vector, any eigenvector for this will have the form. Oops, I don't want to be erasing. So I square root of 15 over 3 and then 1 times some constant x2, which means my eigenspace let's see if I can fit in here is the span of all vectors that look like I square root of 15 over 3 and 1. So notice that in this case, once we had imaginary eigenvalues, we end up getting eigenvectors that are also including imaginary entries, no longer just real numbers. Okay, so if you did it for the other one, so for lambda 2, which would be 1 plus I squared root of 15, you get that its eigenspace would end up being the span of all vectors, and you'd see that it would become negative I squared root of 15 over 3 and 1. Okay, you'd have to take some time to do it, but I trust that y'all have the skills to go through the algebra to do this stuff. Right, so that would be what your eigenspace looks like. And then notice, even still, if I try to test that theory with my eigenvectors, for each of these, we had that theorem that said that they are linearly independent. If I try to solve that equation for linear that I use to test linear independence or dependence, we'd still see that C1 and C2 have to be 0. And so these still, even though they have imaginary numbers in them now, they are still linearly independent. Eigenvectors are always linearly independent as long as you have distinct eigenvalues. Okay, quick questions.
So if it's a multiplicity of 2, then it would be linearly dependent.
What do you mean? What is a multiplicity of 2?
So you just said the eigenvectors are linearly independent as long as the eigenvalues are different. So the only way you can have same eigenvalues is if you have a multiplicity of 2 or more, which would make the eigenvectors linearly dependent.
Yes and no. So, well, the answer would be no. So even if you had lambda 1 and lambda 2 had a multiplicity of 2 or greater. What we're saying with this theorem is lambda 1 will give me some eigenvector. Lambda 2 would still give me, even though it has higher multiplicity, that specific lambda would give me another vector. And when I look at these two vectors, they still are linearly independent.
Well, if lambda 1 and lambda 2 are the same.
Then you'd only be having a single eigenvector, and a single vector is always linearly independent. But good question. Always this fun little playing around with the conditions in our theorems. And that's what makes math fun for some of us, and other people it creates a headache. All right, any other questions? All right, so last thing I want to talk about today leads into our what we're going to call diagonalizable matrices. This is going to be a property of matrices that we look for, because if we can have a diagonalizable matrix, it makes the system, our matrix system, easier to solve. So just a definition, we're going to let A and B be matrices. Specifically square matrices. We say B is similar to A. If there exists a non-singular n by n matrix S such that B is equal to S inverse times AS. And this is how we consider two matrices to be similar. And just to expose you to this notation, usually in mathematics, if we want to say whether or not our similarity is defined in this way or in a different way, depending on what field of mathematics we're working in, that nice little squiggly is usually what we reserve for similar. So B is similar to A or A is similar to B.
Non-singular is non-inversible. I mean, inversible, right?
Yeah. Non-singular means invertible.
So basically, B is the inverse of the non-singular matrix times A.
Times that non-singular matrix. Yep. So essentially A and B are similar. If I can create some non-singular matrix, multiply it on the left by the inverse, multiply it on the right by this weird matrix, and I get the other. This is how we define similar matrices. Okay. And one of the reasons why we care about looking at similar matrices is because there's a theorem. We'll do the full statement because we're out of time. But the theorem that says A and B are similar, and they have these same eigenvalues. Oh, I can't write the S there because there's an icon that my pen keeps hitting. But if B is similar to A, then they both have the same eigenvalues. Put an S there when you write it down. It's actually a cute little proof. I'll see if we can do it on Tuesday. Okay. But this is what I wanted to enter, because when we talk about diagonalizable matrices on Tuesday, when you see it, it depends on this definition. Because what we're going to see is our goal, our overall goal is to, when solving the system of equations, I'll go back to that last slide here in a second if you need it. When solving that system of equations, AX equals B for whatever the system is describing, I want to be able to write this find its similar matrix, but then this D right here is going to be a diagonal matrix. And when it's a diagonal matrix, what we mean is it's just entries only along the diagonal. We're going to see that it ends up being our eigenvalues, whatever they are. We have zeros elsewhere off the diagonals. And if we can do this for a matrix, it ends up making it much easier to solve. So this is a property that we're going to look for, whether or not a matrix is diagonalizable. And if so, we get from being able to calculate, we're going to see eigenvalues and eigenvectors. We get a relatively quick way to end up solving the system. So that's why we're doing this. So make sure you watch the videos for next week. It's up. The two, so what is a diagonalizable matrix and how to diagonalize a matrix. At this point, we're going to try to get into I'm going to try to at least get y'all into the Desmos matrix calculator to help out with some of this stuff. It won't calculate, it will not calculate eigenvalues for you. I just put it in chat. But it can at least do some basic calculator arithmetic for you. So play around with it on your own if you want to. You might be able to use it for the homework to help you do some calculations. I don't think so, though, off the top of my head. But it's an interesting resource for you to have. Because now I know I've seen y'all row reduce, I've seen you multiply matrices, find inverses, etc. I'm going to let y'all use a calculator like this to do it for you. All right. So, promise I'm going to stop talking. Any questions? I said I'd go back to this.
I know we're supposed to have another test soon. What day is it gonna be again?
So I'm probably, and just give you all a heads up for calc, I'm going to try to maybe spread them out by a day or so, but it'd be leading up into the last day of classes. So I would expect it no earlier than, let's say, November 18th. And it will be due probably on the 24th, maybe the 25th of November, just kind of depending on scheduling.
Okay.
I'm double checking that now, but yeah, good question. Any others? 24th is the last day.
All right, you guys have a good weekend.
Me too.